Thank you so much, Eric. And I want to start by just joining my fellow speakers and thanking the organizer for the persistence of still having this workshop. I'm really enjoying it so far. I'm sure the audience is doing so as well. I just want to attribute and give a little bit credit to the people who did this work. So many students, former students and collaborators. I want to especially highlight Hagai Maron, who's a lot of the things you're going to see today are part of his PhD thesis. He recently graduated and moved to video research. So this talk, similar to other talks you heard today, is going to be about deep learning of irregular data. And let me just set up the stage. So irregular data, we're going to think about three different things, or more precisely, three different in a hierarchy of data structure. In the first, we're going to consider sets, which is just a bucket of elements. The elements are usually a bunch of vectors, and vectors in my talk are going to be represented as those colored circles or squares. So each color can be thought of as a feature vector. One higher step in this hierarchy are graphs, where we encode information not only on specific nodes, but also on pairs of nodes. For example, classical graph would have a binary 0 or 1 attached to pairs of elements, but you can obviously attach some more sophisticated information like features on edges. And something which is kind of a vast generalization of those are hypergraphs, where you allow yourself to put information on tuples, subsets of nodes. In geometric deep learning, you can think about the different data as instantiations of these structures. For example, if you take a set and you prescribe a 3D coordinate for each element in the set, you get what is called a point cloud. If you take a graph and prescribe 3D coordinates, maybe on the elements of the set, you're going to get something maybe like a 3D structures of a molecule or whatever. And in hypergraphs, you can do many, many things. For example, you can model surfaces by prescribing nodes, edges, and triangles that consist of small planes. In this case, it's a triangular mesh that kind of approximates the shape of a human body. And our goal, very similar to the goal of other speakers in this workshop, is to build neural networks to deal with this type of data. And the approach we're going to take is based on identifying a natural symmetry of this data. All this data that I prescribed, these data structures have a very natural, even canonical symmetry. And then based on the symmetry, we're going to use the notion of equivariance, which I'm going to define precisely to build neural networks that deal with data. And there's going to be some surprising connections to existing models like message passing, and some statements about the power of the models that we're going to build. So the first thing that we want to do if we want to process or do something with irregular data in a computer, we got to think about a way of representing those in the computer. So the representation is going to be using tensors. So let me kind of define that really quickly. So if you think about a set, so you have a set of n elements. You might want to represent it as a vector of n elements. So basically, sets will be represented as vectors in Rn. Again, the features here are just colors. Everything I'm going to say in this talk has a feature dimension, which I'm going to completely ignore and treat it as colors. If you think about graphs, so graphs basically going to represent it as second-order tensors, where on the diagonal, you plug in the features or the information you have on the nodes. And outside the diagonal, you're going to plug in the information you have on pairs of nodes, i.e. edges. So in case of standard graph, for example, in the off diagonal, you can put something like the adjacency matrix. If you have higher order information, like hypergraphs, so you can think about what is the maximal size of an hyperedge. For example, in this case, it's 3. Then you would need a third order tensors that represent information on tuples of nodes. So one thing, immediately when we set up this way of representing sets, graphs, or hypergraphs, there's immediate question that comes into mind, because vectors are ordered creatures, right? They have order, they are tuples. However, sets do not have an order, right? The order is completely not important. To kind of deal with that thing in the way of building a well-defined neural networks for these creatures, we have to precisely define what things about our presentation we don't care about. So that's called symmetry. In our case, we're going to think about permutations. For example, this is a permutation that switches the first and third elements in a vector in Rn, and applying it to this vector, we're going to switch this yellow and pink feature vectors. So we're going to denote this as sigma of x. That's the application of this permutation to x. And basically, applying all possible permutation, all possible kind of blending of the entries of Rn, going to produce a collection of vectors, an orbit. And this entire collection, we want to think of it as representing the exact same set, right? Because as we said, we want to cancel the extra information we entered to the system by thinking about the set as a vector. The way we're going to do that is thinking about all the permuted version of a set as a set. You can take this one step forward. If we consider graphs and not sets, so graph, we said we're going to represent as matrices. Applying the permutation to a matrix, in this case, exactly the same permutation as in the last slide, would permute the first and third rows, as well as the first and third columns. So applying this permutation basically applies the same permutation to each index of the tensors. If it's a matrix, it's going to apply it to the two indices. So the result of applying this permutation is shown here on the right. Okay, and again, we want to think about all the possible representation of the matrices up to permutation as being the same. They represent the exact same graphs. And now we get to the important question of, okay, and now assume I want to represent a function between sets. For example, a function that takes a set and produces a set. For example, this function kind of identifies there may be the yellow object in the set, for example, or a function between graphs that take a matrix to matrix, or even something more complicated or more exotic that takes sets to graph, graphs to sets, sets to hypergraphs, whatever. The question is what type of property, what property on F would guarantee that we are well defining a function between the symmetric object and not between the vectors, matrices, and so on. So the exact property that is needed is called equivariance. I'm going to instantiate and give this example on sets. So for example, if you have a function on set, okay, and for example, the function, you can imagine the function is, the role is identifying the yellow element. So here it spits out a one-hot vector kind of coloring, putting the probability and high probability on the yellow element. Then equivariance is if you apply this function and then you permute or shuffle the vector, you're going to get exactly the same result as first shuffling the vector and then plugging it into your function. If this diagram commutes, namely that the application of F and then sigma, or sigma and then F, results in the same thing for all possible permutation, we're going to say that this function is equivariant and it is well defined. In what sense it is well defined? It is guaranteed that if you put in a different representation of your set by choosing a different way to order the elements, the function would produce a result in the same, which is equivalent to the output of the original function on the original set. Okay, so this is like a sufficient condition for well-definedness if you want, but it's the most natural one. Mathematically, it's written, basically it says that F and sigma are commuting. And of course, if you think about this definition, it's not really restricted only to set function. You can take an k-order tensors and L-order tensors. So k-order tensor represent information on k tuples of nodes, and L-order tensor, which represent information on L-order of nodes. And then again, applying the same definition would say that F is well defined between those two creatures. It's important to note that this dot here and dot here are not exactly the same, because here the permutation acts on k different indices. Okay, so for example, in matrix, it would act on 2, and this dot operates on L different indices. So for example, if it's set, it's going to be 1. So this definition can also apply to when you increase or decrease the tensor order if you go from set to graph to hypergraphs, whatever you want. So here's, for example, the same image for a graph. So again, basically, I'm not sure this is a very a useful slide, but anyway, you can think about, again, equivariant graph function would be a function between matrices that commute with permuting those matrices according to the rule I just described a few slides ago. One interesting last comment is that if you think about invariance, which means that you want to basically, you're going to give an output which completely ignores the way that your nodes are ordered, then this is a particular case of equivariance where you take the output dimension to be independent of n. So in this case, this dot here acts on just a scalar number, meaning that the only permutation that acts on the scalar number is the identity. Okay, it's like this representation thing. So anyway, I just want to say that invariance is a specific case of this definition. And now we have enough kind of things set up in order to define the equivariant networks. So equivariant networks follow a very kind of natural path. So we start with the most kind of basic structure of neural networks, the multi-layer perceptron, where we have basically a composition of affine and nonlinear function. Each of those gray blocks in my talk going to represent a hidden variable. The input is shown also as a gray box as x, and the output is f of x. And each layer is represented by these black arrows. So in MLP, each black arrow is a composition of an affine transformation applied to the input to the layer, and then a pointwise nonlinearity. And now the idea in equivariant neural networks is basically just to restrict the affine transformation instead to the collection of all possible affine transformations to those who are precisely equivariant or invariant, if you want. And then the nonlinearity is kept the same thing. It's important to note that if you have any entry-wise function, it will be by construction equivariant. That's a small exercise you can do in your head. So you don't have to touch anything about this thing. If we restrict A to be equivariant, then this whole structure is going to be equivariant. If we want to, so this is like used for learning something on the nodes of the graph. If you want to have something on sort of like a classification network, you want to add here an invariant layer. It's enough to have one invariant layer because afterwards everything is going to be invariant. And then you're going to add how many you want fully connected layers or other layers, I don't know, dropouts, what have you. So in order to give a small kind of proof that what we achieved here is an equivariant or invariant network. So if you just use the gray part, you get equivariant. And if you have this addition, you have invariant. You can let's just mark the interior variables by x1 to xk. And then instead of plugging x, we're going to plug a shuffling of x, sigma of x into this network. Since the first arrow is application on affine transformation, which is equivariant, sigma is going to commute with that. It has a pointwise nonlinearity, so it commutes with that as well. And by induction, this sigma is going to be kind of flowing throughout the networks until the last stage, which is going to give an equivariant answer. And if we think about this invariant layer, it's going to kill the sigma, and you're going to get invariant answer. So this is basically constructing a network from basic principle. And of course, equivariant networks is not a new idea. If you think about different permutations, for example, you think about translations, the equivariant linear transformation are going to be convolutions. And repeating this process that I just described would give you the convolutional neural networks. If you think about other group operations like rotations, SO3, or scaling, and so on, there are other researchers, many of them are participating in this workshop, that build equivariant networks to this type of operations, of groups operations. And more specifically related to this talk, we're talking about equivariance to permutations. So there are some classical works from, I don't know, 25 years back that work with arbitrary permutation groups. I want to say that arbitrary permutation groups are pretty difficult because any finite group can be seen as a permutation group. So obviously it's very hard to come up with closed form formulas and concrete networks that you can actually work with. In recent years, we've seen many works that work with equivalent network for specific data structure. For example, a set to set is this wonderful deep sets paper, and PointNet is also relevant. And in this case, they were also able to kind of identify the maximal affine space of equivariant transformations. There were other generalization to tables. However, it seems that for graphs, it was not known what are the collection of affine equivariant transformations. And also, it was the same situation for general tensor to tensor, graph to graph, graph to sets, graph to hypergraphs, and so on. So the first contribution I want to kind of present is basically a classification characterization theorem that basically prescribe and exactly the dimension and a basis for all the possible equivariant linear transformations between k-order tensor and L-order tensor. So this is kind of a generalization of sets to sets, which also includes graphs. So if you have a k-order tensor and L-order tensor, and you think about the equivariant linear operations, it turns out that you have exactly the dimension of this linear space of transformation is exactly of dimension Bell number of k plus n. So in a second, I'll define what it is, but let's take a particular example. So if you think about a linear transformation between a matrix and a matrix, so this is going to be used for constructing graph neural networks. You ask how many independent linear transformations which commute with all possible permutations do I have? Then you're going to have Bell number of 4. So Bell number of 4, so the Bell number is a combinatorial number. It basically gives you it basically counts how many possible ways you have to take a set of k elements and breaks it to subsets. So in case of 4, the Bell number of 4 would be 15. Here I draw all the possible ways that you can break a set of 4 elements to subsets. Let's take 2 examples here. So I guess here one way to do it is put each element in its own set. And here, for example, to put all the elements in the same set, and here divide it to 2 sets like this, and here divide it to 2 sets like that, and so on. So this is a combinatorial number. As you can guess, it increases very quickly, but the important thing about this result is that this dimension is independent from the graph size. So the number of nodes, which is n, does not participate in this dimension. So regardless if you think about graphs with 1 million vertices or graph with 20 vertices, there's going to be exactly 15 parameters that characterize all the equivalent transformation between them. So let's take this one step further and construct equivalent networks specifically for graphs. So specifically for graphs, it's going to be pretty simple, at least conceptually. We have basically it's like an MLP where each arrow is an affine transformation with a ReLU, and each affine transformations be constructed to those 15 or the span of these 15 equivalent transformation. So each of these layers is going to have exactly 15 times the in times the out parameters. Okay, so this is a much smaller than a fully connected network. And in particular, after you learn these 15 parameters, you can apply them to any size of the graph. It's not something that depends on the graph. So although I can train it with specific n, you can apply it to any size of the graph, and that's one of those benefits. So this is a creature. This equivalent networks for graph is a creature that comes up from pretty much a basic principle, and immediately there are a few questions that comes into mind. The first question is how it relates to common and popular models like message passing. So what I'm going to show you in a second, that actually you can actually emulate message passing with those layers, showing that this model is at least as strong. It was recently proved that it is also not stronger than message passing if you keep the dimension of the tensors always 2. And I'm actually going to show you that if you increase the dimension of the tensor, you actually can get models which are strictly stronger than message passing in terms of their approximation power to graph functions. So let me just start with showing how message passing can fall into this framework. So in order to emulate message passing, I think I don't need to convince you that the main thing I need to do is to take the adjacency matrix of the graph and some feature per vertex and understand if I can multiply them using an equivariant network. So the way I'm going to do that is first by broadcasting those vertex values onto the diagonal of the matrix. This is, by the way, an equivariant linear set to graph function. Then we're going to broadcast the values on the vertices to the columns of the matrix. Again, this is a linear transformation that takes this matrix to this matrix, and it's also equivariant. You can actually kind of see that by imagining you reshuffle this matrix by conjugating it with a permutation matrix, and basically the output is also going to be conjugated. And then we use an MLP which multiplies in each feature dimension. So this is per entry here. Multiply this feature dimension with this feature dimension. Okay, again, applying an MLP to each entry is also an equivariant, consisting of equivariant linear operators, which are like the identity. And then summing up the rows and maybe broadcasting them to the diagonal. So we get up this the output here. So summing up the rows and putting them on the diagonal is again a linear transformation, which is equivariant to permutations. So here we modeled one matrix multiplication using several layers of, or approximating it using several layers of equivariant networks. Now, it turns out that if you actually increase the degree of the inner dimension of the hidden variables in this network, you're able to achieve a stronger models than message passing. In fact, you get universality. Let me just kind of state this result. So we actually, in this case, you can take arbitrary subgroups of the permutations, which basically, it's a huge and crazy set. All the finite groups are, can be kind of represented this way. And you can show that if you don't limit yourself in terms that the dimensions, like the order of the tensor inside the network, you can choose them as high as you want. You can basically approximate any continuous G equivariant function. So this is a very, very kind of wide result. However, it's of course not so practical because we never want to work with hidden variables of order, I don't know, maybe higher than 2, because it's going to be extremely memory costly. Okay, so let us go for a second for this case of a graph, and I have here something like maybe 3 minutes to wrap up. I just want to give you like the landscape of how those equivariant networks for graph work. So we have this kind of scale. On the one hand, we have efficiency, the other we have power. The result I just discussed in the previous slide shows that if you allow yourself a very high tensors in the equivariant network, you're basically a superhero. You can compute any function, but it's going to be very far from efficient. If you want to kind of scale things along this axis, one common way that people likes to do it is by thinking about taking some measurements or comparing the graph neural networks to an algorithm hierarchy from computer science called the White-Sfert-Lehmann algorithm. So this is a series of algorithms that tries to tackle the hard task of graph isomorphism, and each algorithm in the hierarchy performs a little better than the previous one. For example, 2WL algorithm cannot distinguish between those two graphs. However, 3WL can distinguish. And 3WL cannot distinguish between these two graphs, which are non-isomorphic, but 4WL can. So if you place your graph neural network algorithm in one of those steps, you're able to kind of compare different, at least in terms of expressiveness, the power of a graph neural networks. So message passing was shown to be in this class of 2WL, and the two equivariant networks is also inside the same class. It's actually, it's also bounded from below, as I showed you, but also from above using a recent work of Chen et al. And we can also prove that if you take K equivariant networks, you have a very nice kind of parallelization between, so you can actually emulate KWL. So K equivariant networks would be as powerful as KWL. So this is really kind of satisfactory. But there's a question of whether you can achieve, for example, something which is strictly stronger than 2WL and stay, let's say, tractable. And the idea, and I'm going to finish in 2 slides, the idea here is that instead of so one thing you can do, you can increase to 3rd order tensors, and then you're guaranteed to be able to implement 3WL and produce 3WL graph algorithms. But instead, you can also enrich the space of transformation. So not only linear equivariant, but also high order polynomial equivariant. And in particular, a most effective quadratic equivariant function is matrix multiplication. If you think about it for a second, matrix multiplication is quadratic equivariant. And it turns out that if you use it on 2nd order tensors, you can already achieve 3WL power. So here's my last, I guess my last slide, because the time seems to be running out. So here's a graph neural network. A super simple one, would consist of layers of the following form. You apply MLPs to the feature dimension in the input tensors, and then you matrix multiply corresponding features, just a regular matrix multiplication, and you concatenate the result. So here you have a code in PyTorch for this layer. You can stack several of those, and you can actually prove that this very simple graph neural networks is strictly stronger than 2WL or message passing for that end. And that's it. Yeah, there's not much things to say about the results. And I'm going to skip this slide as well. Sorry for being a little bit over time.
Don't worry, we started a bit later.
Okay, all right. You know what? So I'll just say one more thing. Sorry. So I just want to say that there's an interesting question. If you think about graph-to-graph functions, basically the previous slide showed you that this is a kind of a difficult task. At least we still don't have a universal graph-to-graph functions which are also tractable. We need extremely high tensor orders. And on the other hand, we know that set-to-set are universal. So there are simple models like deep sets, which are equivalent universals. And there's an interesting question that deals what happens if you think about function from set to graphs. Would that be easy as set to set or hard? When I say easy, hard, I mean in sense of establishing a universal models. So it turns out that this is the difficulty comes from the domain and not the target. So the set to graph functions are actually easy, not very far from set to set, and you can come up with equivariant models which are universal very cheaply. The models are similar to classical similarity learning algorithm, but have a small twist. And I invite you to look at the paper if you're interested to see how to do that. The different papers I covered in this talk are shown here. And again, sorry for being a little bit over time, and thank you again for organizing this workshop.
Okay, thank you very much, Yaron, for this wonderful talk. So we have time for maybe 1 or 2 or 3 questions. Try to keep it short. So there's one question which I find very interesting, which also came to my mind. It's by Clément Vignac. He asked the question: the fact that the dimension of the space of linear equivariant functions is independent of n looks a bit magical. Do you have an intuitive explanation for why it holds?
Yeah. So the idea is that basically, as you increase the size of the group you want to be invariant to, you basically decrease the number of elements that you are left with equivariant. So you can think of it as some sort of like a division. So the dimension of all the linear transformation divided by, in some sense, the size of the group. So here's an example that many of us know. So if you think about convolutions, right? So if you have convolutions, the group that we're talking about are translations, right? And translation can take, for example, any pixel in the image to any other pixel. And we think about transformations that are equivariant to translation. We have convolutions. And in convolution, we reduce our dimension from n's, like the number of pixels squared, to just the number of pixels. Okay, so we reduce 1 order of magnitude. Now, permutation is much bigger group than just translations, right? So it turns out that the permutation would decrease the number from being linear in the number of pixels to just constant. Okay.
Okay, maybe another question relating this. So in the group convolutional setting, you have similar theorems, right? That constrained linear functions, they lead to convolutions and group convolutions. And what is typically done is that you augment your space with the size of the group. I think that's the Bell number in your case. Is that sort of what's happening? That instead of applying your function once, you apply it for every possible permutation and then continue with these higher dimensional things, keeping track of the indices?
I would say that's, I don't think that's, so I guess you're referring to the fact that you lift, like in your work, you lift your function to a function over the group or something like that. And then the convolution has some natural definition over the group. Here, actually, I don't think that's the case. The representation of the data is never existing on the group. The group is too huge and discrete. So what happens here that when we increase the dimension that I talk about tensor order, it's not really that we encapsulate things on the group. It's just we look at creatures with a different symmetry. So a matrix has different symmetries than a set, right? But it has the same group that it's a different representation of the same group. So permuting an element of a set or the rows and columns of a graph and so on is an incarnation of the same group, but in different elements. It doesn't make sense.
Yeah, I think that makes sense. Thank you a lot. There's another question coming from the YouTube channel by Sergej Mishakin. He asks, is there a successful application of this theory for point cloud matching that work better than classical approaches, for example, iterative closest point?
So as I said in the beginning of the talk, point clouds are basically sets, and the point net is really an instantiation of the equivariant network, which works on set. And I think now almost all papers we see on point clouds and matching of point clouds involve point net inside or deep sets. So it's basically the same thing. So the answer is yes. I think we. For sets, it's a huge success, and people use it, I think, all the time.
Okay, wonderful. Yeah, thanks for the answers, and thanks for a great